Okay, so let's start. So today in this lecture, we are going to discuss the differentiability of some important function, some special function like greatest integer, modulus, signum, and fractional part. So here we are going to discuss differentiability. In last video, we discussed about continuity of all these four functions. In this video, we will discuss differentiability. So before discussing differentiability of these some important functions, we will discuss what is the basic definition of differentiability, and we will see also when a function is not differentiable. After that, we will see the differentiability of all these functions. So first, we will discuss about differentiability. Okay, so suppose we have a function y equals to fx. Okay, we have a function y equal to fx. So let's draw it. So suppose we have a function like this one. Okay, this is y equals to fx. So go through in the past, that is class 10th, we discussed about slope of a line, right? So slope of the line, how can we find the slope of line? That will be of, suppose we have a straight line, then we can find the slope of this line by 2 points. Suppose we have 2 points. Suppose this is x1 and this is x2, this is y1 and this is y2. Okay, so slope is defined by y2 minus y1, x2 minus x1. So this was the slope of a straight line. Okay, here we want to find the slope of this curve, but this is not a straight line, like this is a curve. So suppose we have a function like this is point A, then this will be of fa, right? Function's value at A, and suppose this is point A plus h, then this will give fa plus h. Okay, and we will take here a minus h, then this is fa minus h. Okay, here the distance is like in, but this is understandable that this is okay. Let's make it clear. This is your A, this is fa. Okay, so see, we want to discuss the slope, like existence of tangent for this function. Okay, so if we see a line like this one, suppose this is a line. Okay, so this line cuts the graph at 2 points, at 1 and 1 a plus h. So this line becomes tangent. When this line becomes tangent, when this point P and Q overlap to each other, comes close. Okay, this line PQ will become the tangent line to this curve whenever this P and Q will merge at a point. Okay, and for this, the distance which is h, that should tend to 0. Okay, so the value of function is at a fa, at a plus h, fa plus h, and this distance is h. So we want to find the slope. So when this slope, like existence of tangent, when p goes to q, okay, and that means h goes to 0. So now what is the difference between here y values? That is fa plus h minus fa. Okay, and here what is the difference? H, and here limit h goes to 0, means this line will become tangent whenever h goes to 0. Okay, so this is the limit we are looking for from right side. Now for left side, we can clearly see f a minus h minus fa upon minus h, limit h goes to 0. So if these two limits exist and equal, then this tangent line will be unique. Why unique? See, if we are going to see the slope of this tangent line, then this will give the slope of this line, tangent line, that is existence of tangent from right, and this will give the slope of tangent line which is approaching from left. If both are equal, then both will denote same slope, that is left tangent and right tangent, that is slope of left tangent, slope of right tangent will be same, and that is the concept of unique tangent. Okay, so differentiability means a function will be differentiable at some points whenever it has a unique tangent at that point. And a unique tangent means you should have a unique slope. Unique slope means from left and from right, this will give the same value. This is called LHD, RHD, and this is called LHD. Right hand derivative, left hand derivative. Right hand derivative will give you the slope of the function from right, that is also we can say right tangent, and this is slope of the tangent, that is left tangent. If both are equal, then the function will be differentiable at that point. Okay, so the concept is LHD equals to RHD. This will imply both exist and equal. This will imply function is differentiable. Okay, that is concept of unique tangent. Okay, so differentiability is very simple. The meaning of differentiability is existence of unique tangent. Okay, so we will calculate LHD, we will calculate RHD. If both exist and equal, then the function will be differentiable at that point. What is LHD? That is limit h goes to 0, fa minus h minus fa upon minus h. What is RHD? Limit h goes to 0, fa plus h minus fa upon h. And if we see, then both limit are associated with a single limit, that is limit x goes to a, fx minus fa upon x minus a. So we can see that this limit should exist for differentiability, and for this that will be left hand limit, that is right hand limit. Okay, so if you can see that this limit directly exist, then the function will be differentiable. Okay, and if you want to see the existence, then you have to find LHL and RHL, which is called LHD and RHD here. So function will be differentiable. So this is the only case where function will be differentiable, that is LHD, RHD must exist and equals to equal. Okay, both should be equal. Now our point is to check the non-differentiability, where the function is not differentiable. So we will see here that when a function is not differentiable. Okay, when a function is not differentiable, right? So here we saw the definition of a geometrical interpretation of differentiability that is related to the unique tangent, that is left slope and right slope should be equal. Left tangent slope, right tangent slope will be equal, then function will be differentiable. So overall we have to see that at some point where you have to check the differentiability, the function has unique tangent or not. If function has unique tangent, the function is differentiable. If function has not unique tangent, then not differentiable. Okay, so now we will write the points that when a function is not differentiable. When a function is not differentiable. Okay, we want to find when a function is not differentiable. First point is, if function is not continuous, this will imply f is not differentiable. If function is not continuous at any point, then directly we can say that the function is not differentiable at that point, because continuity is the necessary condition for differentiability. Okay, if you want to check the differentiability of the function at any point, then use the function should be continuous at that given point. Okay, so necessary condition for the differentiability is continuity. Second point is, left hand derivative is not equal to right hand derivative. If we calculate left hand derivative and right hand derivative and both are not equal, that means the function has two different slopes at that point. Left tangent has different slope and right tangent has different slope. That means function is not differentiable, because at that point you cannot find the unique tangent. Okay. Now third is LHD and RHD does not exist. Okay, so if LHD and RHD does not exist, then we cannot find the left tangent slope and right tangent slope, so function will not be differentiable at that given point. Okay, now fourth point is kink or sharp corner. If function has a very sharp corner or kink at some point, then function will not be differentiable at that point. Okay, so for example, we can see that this graph, has a corner kink. So at that point function will not be differentiable, but we want to find the reason why the function is not differentiable at sharp corner, and that is very simple. You can see that if you have sharp corner, then at that point there is existence of two tangents, tangent 1, tangent 2, and there are two tangents means the two slope, so there will not be unique tangent. That why at sharp corners the function will not be differentiable. Okay, now the fifth point is, we will write it in the next page. Fifth point is vertical tangent. Okay, if at some point graph has vertical tangent, then the function will not be differentiable at that point. Okay, so suppose we will draw the graph of a function. Suppose we have a function and we here draw a line and like this one. Okay, suppose this is a function like this one. You can see that this function has a tangent line, vertical tangent line. This is vertical tangent line. Vertical tangent line means tan 90 degree. The slope of the tangent will be 90 degree, and we know that tan 90 is not defined. That's why if any curve has vertical tangent, then at some point, suppose at x equal to a, then that function will not be differentiable at that point due to vertical tangent. Okay, so these are 5 points where we can see that function is not differentiable. Again we will repeat this. So first one is continuity is the necessary quality for the function. If function is not continuous, then function should not be differentiable. Function will not be differentiable. Second point is, if left hand derivative is not equal to right hand derivative, then function will not be discontinuous. Third point is existence of left hand derivative and right hand derivative. If left hand derivative and right hand derivative, any one of them will not exist, then function will not be differentiable. And fourth one is kink or sharp corner. If graph has some sharp corner at some point, then function will not be differentiable at that point. And fifth one is vertical tangent concept. That is, if a graph has a vertical tangent at some point, then you cannot discuss the differentiability at that point. Function will not be differentiable at that given point. Okay. So these are the 5 points where we will see the function is not differentiable. Now we will discuss the differentiability of greatest integer, modulus function, signum function, and fractional function. So now first, greatest integer function. So as we know, greatest integer function is not continuous at integer points. So we will know that the necessary condition for differentiability is continuity. And if function is not continuous at some given point, then function will not be differentiable at that given point. So for x belongs to integer, if x is integer, then function will not be continuous and hence function will not be differentiable. Okay. So for x is integer, the function will not be differentiable. Suppose we have greatest integer function, this one. So when fx is integer, this will imply greatest integer fx is not continuous, and this will imply not differentiable. Okay, because if function is not continuous, then why I should check the function is differentiable or not. So clearly in last video we discussed that greatest integer function is not continuous at integer points, hence not differentiable at integer points. Now move to the second one, that is fractional. Fractional x. So also fractional x is not continuous at integer points, hence it is also not differentiable at integer. Okay, and apart from integers it is differentiable. So clearly fractional x is not continuous at when x is integer, hence not differentiable at integer points. Okay, suppose we have a function, we can take an example. Suppose we have a function like fx equals to fractional x sin x. Okay, so whenever sin x is integer, then this function will not be continuous and hence not differentiable. So we can see that sin x takes only 3 integer value, that is 0, +1 and -1. So when sin x equal to 0, 1 and -1, this function will not be continuous and hence not differentiable. Okay, so this is very obedient and simple. We can check the differentiability of fractional part of x. Okay, now move to the third one, that is modulus function. So now this is very interesting, modulus function. So modulus function is always continuous, we know that. So we can discuss further more for differentiability. Okay, so y equals to mod x, that is when x is greater than or equal to 0, x is less than 0, minus x, and the graph of this function you can see that like this one. See, so clearly you can see that this function is always continuous at every point. Continuous at every point. Continuous at every point, that means continuous on R. For every point, modulus x is continuous. Now we want to see the differentiability of the modulus function, and here we have 2 ways to check the differentiability of modulus function. One is by graphical and another is by the concept of left hand derivative and right hand derivative. See, if we see the graph of modulus function, you can see that at x equal to 0, the function has a sharp corner, at x equal to 0, function has a sharp corner, and that's why mod x is not differentiable at x equals to 0. So whenever x equal to 0, this modulus function is not differentiable. Okay, so here we can see the corner. So we have two tangents, this one like this one. So not unit tangent, that's why function is not differentiable at x equal to 0. Now we will see the not differentiability of modulus function at x equal to 0 with the concept of left hand derivative and right hand derivative. So first we will calculate left hand derivative at x equal to 0, right? So this will be limit h goes to 0 f a minus h, that is 0 minus h minus 0 upon minus h, and this is equals to limit h goes to 0 h upon minus h, and that is minus 1. And again RHD at x equal to 0. So what is RHD at x equal to 0? That will be limit h goes to 0, 0 plus h minus 0 upon h, and that is limit h goes to 0, h upon h, and this is 1. So you can see clearly that left hand derivative is not equal to right hand derivative. LHD is not equal to RHD. That's why this function is not differentiable at x equal to 0. So we have a concept. Whenever we have any function under modulus, okay, for example, we have a function fx under modulus, then this function will be not differentiable where this fx is 0, okay. This is very simple concept. Whenever fx equal to 0, the function will not be differentiable, okay. So we will see some examples by which we can see that how we can discuss the differentiability of modulus function, okay. Okay, so I hope this concept is clear to you. By left hand derivative and right hand derivative, we can also see the differentiability of the function, as well as we can see the by graph that at x equal to 0, graph has a sharp corner. That's why the concept of unit tangent is not applicable, and hence function is not differentiable at x equal to 0. Now we will see examples like, first example is fx equal to mod x minus 2 plus mod x minus 3 plus mod 2x minus 1. Suppose you want to discuss the continuity and differentiability of this function, then this is modulus function, modulus function, modulus function, and under modulus function you can see this, all these are 1 degree polynomial, hence this function is always continuous, okay. So if we discuss continuity, then always continuous, that is continuous at every single point in real line, okay. Now we will see the differentiability. So mod x minus 2 is not differentiable when x minus 2 is 0. So mod x minus 2 is not differentiable when x minus 2 equal to 0, that is x equal to 2. Similarly, mod x minus 3 is not differentiable when x minus 3 equal to 0, that is x equal to 3. And finally, mod 2x minus 1 is not differentiable when 2x minus 1 equal to 0. This will imply x equal to 1 by 2. So this function is not differentiable at x equal to 2, x equal to 3, and x equal to 1 by 2. At these 3 points, this function is not differentiable, okay. I hope it is clear to everyone. Now move to the next question. Simply you have to equate the 0 which function is under modulus, okay. So fx equals to mod of 1 minus mod x, okay. We want to discuss the differentiability. It is always continuous because modulus function is always continuous. So we are not going to discuss continuity. We are going to discuss differentiability directly. So we have two ways to check the differentiability of this function. One is by graphical method, another is by concept that this function must be 0. Okay. So first we will see the concept. What is the concept? Fx must be 0. Okay. So under this modulus, the function is 1 minus mod x. So 1 minus mod x equal to 0. So mod x equal to 1. So x equal to plus minus 1. So here we can find x equal to plus minus 1. But if you see, then there is another modulus, that is mod x. And we know that mod x is not differentiable at x equal to 0. So also when x equal to 0, then function is not differentiable. So we got 3 points, x equals to 0, 1 and minus 1. So this function is not differentiable at x equal to 0, 1 and minus 1. This is the concept method. Now we will see the graph. Okay. So first we will draw the graph of mod x. This is mod x. Okay. After mod x, this is minus mod x. So this is y equals to mod x. Now minus mod x is like this one. This is minus mod x. Okay. And after that we have to add 1. So if we add 1, then graph will be like this one. This is plus 1. So this is 1 minus mod x. Okay. And finally we will draw the graph of this whole function. That will be like this one. This part will be goes above the x-axis, and also this will go above the x-axis. So this is the required graph of this function. Okay. And clearly you can see that there are sharp corners at here, here and here. So at x equal to 0, we have sharp corner. At x equal to minus 1, we have sharp corner. At x equal to plus 1, we have sharp corner. So at these 3 points, we can see that function is not differentiable. Due to sharp corner, there will be 2 tangents. That's why the concept of unique tangent will not be applicable there. Hence, the function will be not differentiable at x equals to minus 1, x equal to 0 and x equal to 1. Okay. So at these 3 points, the function is not differentiable. So in this question, we discuss the differentiability of this function with the help of graph as well as with the help of our concept. Okay. You have to just equate to the 0 to the modulus function. Okay. Fine. Now the last function is Signum function. Fx equals to Signum x. Okay. So graph of Signum x, you can see that this is plus 1, this is minus 1 and at 0. So at x equal to 0, Signum x is not differentiable. We know that. At x equal to 0, Signum x is not continuous and hence not differentiable. Okay. So if we have a function like this one, Signum of fx, and we want to check the continuity and differentiability of this function, then it is very simple. You have to just equate the function fx to 0 and solve that. You will find the value of x, and for that value of x, the function will not be continuous as well as not differentiable. Okay. So for differentiability, you have to just do that fx equal to 0. So whenever fx is 0, the function will not be differentiable, and you can easily find the points where this function is not differentiable. So I hope you learned the concept very well. We discussed about differentiability. First we discussed about concept of differentiability. After that we discussed about differentiability of modulus function, Signum function, greatest integer function, and as well as fractional function. So fractional function and greatest integer function are not continuous and not differentiable at integer points. Signum x and mod x both are not differentiable at x equal to 0 That is, whenever we have signum fx or mod fx, then just equate fx equal to 0 and you can find the point of not differentiability. And modulus function is always continuous. Okay. So this was our concept.